Tarzan swinging on a massless rope, so his center of mass stays a distance r from the fixed support. He's initially at rest at an angle b sub I. And then he lets go of support. Assume his mass is m, and we have two questions to begin with. And the question is, what's his velocity when he goes from b sub I to b? And there's two different cases. Case number one, he's holding on to the rope such a way that as the rope is turning and rotating, his body is also swinging with it. Case number two, he's holding it such that his head's always up, he's always heading his orientation. So what's the velocity when he gets to B for case one? What's the velocity he gets to B for case two? And then the next question would be, what's the force on the rope when he gets to angle beta for case one and case two? Pause the video, solve the problem, and I'll have an answer, and then you can compare answers, and then I'll solve it. Answers, we'll start with case one answer on the velocity of Tarzan's center of mass in the final state. Square root of 2gr cosine of beta minus cosine of beta initial, and this r cosine beta minus beta initial is really delta h. Case one, where he has some, his center is changing orientation, so he has a rotational term about his own center of mass. In this one is 2gr, same cosine of beta minus cosine of beta initial, but it's divided by 1 plus the moment inertia of Tarzan about his own center of mass in the z direction divided by mr squared. For the forces on the rope, for case two again, the more simple one where he's staying in this orientation, is mg times the quantity 3 cosine beta minus 2 cosine of beta initial. And for case one, you can see two alternative forms, and both of these again have the term of the moment of inertia of the Tarzan around his own center of mass in the z direction. If you got those, great. If you didn't, I'll go through the solution. Starting to solve now. Pick a system. Let's pick Tarzan. Make some assumptions. Let's ignore the frictional drag force of the wind, ignore any buoyancy force, ignore any frictional rotational things that on the support that prevent anything from happening. Now let's draw a free body diagram of Tarzan. So what forces on the surroundings act on Tarzan? I drew those in orange here. So we get gravitational force, mg, and we have a rope force pointing along the rope. That's all the forces that act on Tarzan with these assumptions. And then thinking about, well, kind of what's Tarzan doing at any point? His center of mass has some velocity here, kind of perpendicular to the rope. So this is not a force, but momentum, which is his mass times v. And you think about it as an object its center of mass is revolving around a point. Work is integral f dot dr, and for this thing about rope, the rope force and the dr, his change in position at any moment of time, they're perpendicular. So F rope does no work on Tarzan. And so this would be true for, let's say, the Earth, sun revolving on the Earth. There's no work done on it. It's free. There's case. I mean, other case, cylinder with pure rolling down a hill. There's no work done between the frictional force and the ground. So there's many cases where we have forces acting, but because the motion is perpendicular to that force, there's no work done on it. And so that thinking about that I don't need to worry about that rope force as far as work being done on it. Thinking that the question doesn't ask anything about time, it just asks what's his velocity when he gets to here. Thinking about with all these assumptions, so if Tarzan let go here and he's swaying down and he'd come back to the exact same point, because I'm saying there's no friction or there's no air drag. So, so energy seems like a good way to go to try to solve this problem. So let's try to solve this problem using energy methods. If you didn't think about that, pause the video now and solve it using energy methods as far as you can go. Using the energy principle, then, we know energy final equals energy initial plus the work plus the heat transfer into it. We have no heat transfer in this problem, so that's going to 0 for this case. I personally like, if I have changes in height, to use potential energy other than work. Work works great if you know force. We know force acting on him downward from gravity. His motion is going to be down, so we know work's going to be positive. So it's great to do that. So we have a positive term over here. If you say the system's Tarzan and the Earth, then it's all potential energy due to gravity. So either way, fine. Either way works. I'm going to do it saying the work on the system. I'm going to say Tarzan and the Earth are now the system, because it's easier for me, and I can consider potential energy. So energy, all its forms. So we have rest energy initial and final are going to be the same, so really you can probably ignore that, don't even need to talk about that. We have kinetic energies, we can have translational or rotational values. For case A, the center of mass has velocity, and for case A, we're assuming that he has some moment of inertia about his own center of mass. So therefore, there will be rotational as well. For case 2, he's not rotating, so that wouldn't be there. But we're going to solve for case 1 here, general, so let's consider that. Potential energy in the final state, we could have gravitational, spring, electric, anything which is path independent. We don't have the electrical or the spring, but we do have gravitational. And then in the final state again, initial state, translational, rotational, and potential energy, and work on the system, and we're saying that was going to 0. And if my system is Tarzan and the Earth, then we know this does no work on it. I'm going to include this as potential energy, so we know that there's no work on the system since I picked Tarzan on the Earth. So now putting in terms, in the final state, kinetic energy 1/2 mv is center mass squared final. Rotational kinetic energy 1/2 I around the center of the mass, and here he's rotating in this outward direction, so I'm going to call this one, picking a coordinate system is important. For a problem like this, it's convenient to pick a coordinate system that is parallel to his motion, one that's perpendicular to his motion, and then you have the other one. So I'm going to call this the x direction, this is the y direction, and the x could be parallel as well, y perpendicular, and z. So the moment of inertia around the center of mass around the z-axis times the final angular frequency squared. Now, so kinetic energy at the beginning were 0, so those are there. Now think about potential energy of gravity. So you can either have values here or here, but kind of there's a delta potential energy that's happening. So looking at it graphically here, he started out at this position, he came over to here, the angle changed to beta, r stayed the same. So if you do the trig, you can see in the initial state, kind of this length Li is r cosine beta initial, and this length in the vertical at the final is r cosine of beta, and we know he's higher at the initial condition than is in the final condition in the picture is shown right here. So he had more potential energy here than he had here. So we know that initially he had more potential energy than he did final. So I could put a value in here, or I could just talk about potential energy is relative to some reference. So if we kind of had the reference is this final state, and said he'll have more potential energy in the initial state. Since H initial is greater than H final, we know the potential energy due to gravitational is higher initial than final, so we can just have this term here, call that, so we can call this 0, and make sure this number here is a positive number, and that's going to be due to this delta. So that's mgh, and we'll call h 0 here. So this delta height here, well, the height difference between initial and final is the difference between these two values, and double check it, make sure this turns, cosine of beta here is going to be greater number than cosine of beta initial. So that's going to be positive, this is positive. It all makes sense that this is positive. We also kind of know, if we consider it to be work, that the mg is, if I didn't do a potential but I did work instead, I would add mg times the delta, the change in well, it's F cross R. F is mg, the R is this delta R. Delta R is in the same direction as mg, so force and displacement are the same direction. We know work would be positive. So if I said the system was Tarzan and those would have been 0, work on the system would have been positive. So I screw up on that a lot. So think about it, but both either in the work, using the work method or the potential energy method, this is the value here, and it's positive because it's greater on the initial condition, or consider the work being done in the system is positive because the mg dot delta r, they're the same direction, so that work done is positive. So this equation's resolved either way, either if I have system Tarzan or system Tarzan Earth. You can see there's my new equation. I know for something rotating that the velocity center of mass magnitude is r omega, so omega is velocity over r. I can substitute here for omega final squared is v squared over r squared. You can see now I have common v squared terms. I can group these. That's this side. I can do the algebra, and here I get, and for case 1, there's my velocity of center mass final. I could divide both sides by m, sorry, and I would get this term right here. So either one's equivalent. Okay. Case 2, pretty much the same concept. The only difference is case 2, this person's not rotating about his own center of mass. Tarzan's not rotating, so this term goes to 0. I don't have this term for case 2. So case 2, this is 0. Okay, we don't have that term, so it's just simply this. And so one could solve this rest of the equation the same way, but I don't need to do that term. And so I can find out, again doing the algebra, so this is my velocity of center mass. And you can see when I initially solved it, I had an m over m, and then I can divide those out. So you can see for case 2, the velocity center of mass doesn't even depend on his mass, which kind of makes sense. That's this thing coming down, that the velocity is mass independent. And then if we want to look at angular frequency is just the velocity of the center of the mass divided by r, so that's angular frequency. And then you can compare these two answers. You can see that if I do have some moment of inertia about center mass and it's rotating, then this is going to be some value greater than 0. So for case 1, the velocity center mass would actually be less than for case 2. So these are my two solutions as far as velocity to the center of the mass. Now, if you didn't get that right, think about it, and we can pause and solve for 3. Trying to solve for the force in the rope, we know that work probably and energy is not going to be a good way to do it, because again we mentioned that the dr, or the change in the motion and the force of the rope, they're perpendicular, so the dot product would be 0. So energy and there's no work, there's no energy changed by this force in the rope. So we need another principle. Let's think about momentum. Momentum and force are related. We know this man has momentum gamma mv, just call mv here. We know potentially he's speeding up. We know his velocity final is higher than his initial, so we know he's got some change here in magnitude. We also know that he's pointing this way. I mean, the center of mass is here, and then the center of mass his velocity was here, and then his velocity is changing. It's perpendicular to the rope, so it's changing there. So think about momentum. It's its magnitude times its direction. Force is related to change in momentum. If I use the product rule, I can the magnitude change or the direction change. This is the magnitude change again, and then from a previous video we've seen that the change in momentum direction versus time is omega in a vectorial direction perpendicular to p. So we know that here's my momentum parallel to its motion. My dp dt is the magnitude change in p versus time, and then perpendicular to p. So p was here, and then p is going to be sometime later spinning around here. So going towards the center of p, the magnitude in the perpendicular direction to this p vector this time is the magnitude of p at that time times the angular frequency of how that p vector is changing, which happens to be the same. Is the same omega as what this rope is doing, because as the rope's spinning and he's spinning, this p vector is changing the same way. So if you haven't solved it already, think about this as the way to solve for the force. Using a momentum principle, we know that the change in momentum in any direction is the net forces on it. So let's think about it in the perpendicular to motion direction. So at the net condition, the change in momentum versus time is momentum magnitude times the angular frequency. Okay, and so the net forces, so we'll call this the positive perpendicular directions there. I have a force on the man from the rope. That's vectorially in that direction. And then looking at the component of the mg term, which is in the perpendicular direction, so that's mg cosine beta, and that's in the minus direction. So these are the net forces acting. Here's my change in momentum versus time perpendicularly. We know momentum is gamma mv of center of mass. We know omega is velocity over the radius for this condition. So this term right here, I can have mass, velocity, when I do this, the algebra, velocity squared of center of mass over r, or m omega squared r. We know from any of these cases here, we know the velocity center of the mass. So so here's ultimate what this becomes. This was my change in momentum versus time perpendicularly. Here's my net forces. I can solve for f of rope. Bring this over here. So there's my force of rope. I know my velocity of center of mass, so I can just substitute for case number one. I can substitute this value in here, and do some algebra. I would come up with this for force on the rope. For case number two, this is my velocity center of the mass, so it comes a little bit simpler. I'm not doing the algebra for you here, but you can see the force on the rope is mg times the quantity 3 cosine beta minus 2 cosine beta sub I. And just as a check, maybe think about this one. If and this is true for at any beta final. So I mean, if beta final here. So let's say beta initial and beta final are the same thing. So these cosines would be the same. So 3 minus 2 would be 1. So the force on the rope at the initial time, before he even starts to move, would be mg cosine beta, which if he has no momentum and there's no change of momentum at that time, you can see that vectorially works. So there's a check on the work that makes sense.